Welcome everybody. This will be a lecture on weight update rules for neural networks, various possible schemes in this course on intelligent control. We have already discussed various feed-forward neural networks, multi-layered neural networks, radial basis function neural network, and associated algorithms for these networks. Also, we proposed in the last class a very interesting algorithm for weight update, that was the adaptive learning rate using Lyapunov function. So, we will now summarize the various schemes that are being employed to improve on the convergence property as well as the global convergence criteria for minimizing a cost function given a network. So, it would be a kind of a summary to let you know what is the state of art of various weight update rules for specifically feed-forward networks. So, topics that would be covered today would be conventional training algorithm, gradient descent that we have already been talking about, which is popularly known as back propagation algorithm for feed-forward networks, Newton's method, Quasi-Newton method, conjugate gradient method, and these methods would be kind of compared with our schemes also that we proposed last time. That is our personal work, the work of our group at IIT Kanpur on adaptive learning rate, and then we would kind of summarize everything that we have learnt. So, introduction. Feed-forward neural networks are used as function approximators for learning mappings between input and output space, right. A neural network is represented as y equal to fwx, that is, if I have a neural network here, this is some neural network, then my output vector, okay, is y and input vector is x. Neural network is characterized by weight vector w. Then my output of neural network is a nonlinear function of weight vector w and input x. Weight vector w is updated in such a way that a specific cost function is minimized such that network can predict for the test data. So, we give some data, we generate some training examples for this network for training, and then with another set of such examples we test the predictability of this network. Desirable features of learning algorithm: locating global minimum of the cost function, first convergence, good generalization, that is learning from minimum examples. So, I take minimum examples and then this network learns network is provided with minimum example, and from that example it can if the network can extract the map of the entire data that is there in input output space for that specific domain, and the prediction is pretty nice. So, then that is a good generalization. Less computational complexity. So, this is very important, we do not want to have an algorithm that takes a long time for computation, so very fast, like back propagation algorithm with all its drawbacks is very fast. It is simply a first order approximation of Taylor series approximation, the back propagation that tries to minimize. So, it is very fast, this algorithm is. So, the traditionally that people have tried to propose various algorithms for feed-forward neural networks, including the even feedback neural networks that we have already talked. All these things can be applied both to feedback and feed-forward network for system identification, because we are talking about intelligent control. So, when we talk about neural network, we are talking in terms of either system identification or control. So, all these gradient descent, Newton's method, Quasi-Newton method, conjugate gradient method, all these methods, the variant of these methods have been applied to neural network to varying degree of success. So, cost function, normally a cost function is a function of a weight. You see that this is so while training a neural network, the cost function is usually written as this, where this is your desired output, this is your actual output predicted by the neural network, and then for MP is stands for pattern. So, if I have n patterns, so this total error, square of the error should be minimized. This is not the normally this is a quadratic cost function, but not necessarily we go for this function, but usually researchers they use this kind of function, this function, this type of function. And here if you look at what is YP, this YP is the output of the neural network, and YP is function of neural network weight, and XP is the neural network input. Okay. So, this XP is input, YP is output, and so in that sense you can easily see that E is actually a function of W, because since YPD and XP are known. Given a training example, given a training set, then I know what is YPD. In YP also this function I know what is XP. So, all that I do not know is the weight vector. So, in that sense my cost function is simply a function of weight vector. Thus, E is a nonlinear function of weight vector W, and it will be represented as EW. You understand why we are writing EW, means E is a function of exclusively a function of W when we train a neural network. The objective of learning is to find W star such that EW star is optimized or minimized. Usually we minimize the error. So, recursive form of a general learning algorithm is weight vector new is equal to weight vector old plus delta W with an initial condition W naught. Okay, we start with some initial condition. So, now let us talk about gradient descent. I mean, what we are trying to do in this lecture is that I would like to give you a comprehensive picture of all this learning algorithm that we are being talking about until now. So, let us talk about a gradient descent algorithm. What is actually a gradient descent? What it does? We understood in our previous discussion, it certainly does not take us to, or it does not guarantee us to global convergence, or theoretically the gradient descent cannot take us to a gradient descent, to the global minimum. Okay. So, that is, if we have a cost function like this E and this is W. So, obviously if I start from here I may reach here, if I start from here then I may reach here. So, it all depends on the initial condition where I am starting, and since I do not know where is the global minimum, so how can I fix a initial condition that will be very near to the global minimum. So, it is very difficult. No theoretically gradient descent cannot ensure global convergence, it only ensures local convergence. So, in that sense what gradient descent does. Let us think about the function that we talked about, that we are trying to minimize, EW, error function. So, if I expand this error function around W naught, okay, some initial point, okay. So, and I do a Taylor series expansion, then you see that EW naught plus delta E by del W delta W first order, second order term, that is del square E by del W square delta W square, this is whole square actually, and plus so on. So, this is the series what we are talking about, and if we neglect in this expansion second order and higher order terms, that is, if I simply consider the first order Taylor series expansion of the cost function, then this is my expression. Okay. So, the approximation first order of this is first order approximation of EW. Okay. First order Taylor series expansion, TS. TS is Taylor series. So this is this is what we have written here, Taylor series. So this Taylor series expansion of the cost function, the first order Taylor series, looks like this particular which is given in this block. Now, if I select delta W as minus eta del E upon del W transpose, right, you know that E is a scalar. When I differentiate a scalar with respect to a vector, it becomes a row vector. So, transpose makes it a column vector, and delta W is a column vector. Okay. So, we get if I replace this delta W, this particular expression, in the previous expression, and that expression is that we wrote earlier, E hat is E W naught plus del E upon del W in delta W. So, in this, replace this delta W by this minus eta del E upon del W transpose. So, if you do that, then E minus EW will become this quantity, because if you take this one here, so you get minus eta del E upon del W norm square, and since this is a norm quantity which is always a positive quantity, so hence this this particular term is always negative. What it implies? It implies that if I start from W naught, the next W, the update, would be always less than EW naught. Okay. So, that is, again, when this W will become the initial point and you go to the next point, so it will always decrease. This would always decrease, because the it will always decrease. In which sense? The decrease is ensured only when in terms of the when EW is looked at as a first order approximation of Taylor series. Okay. But this is not always, if this is not true, I can't say EW is less than equal to EW naught. This is E hat W, and E hat W is a first order Taylor series approximation of the cost function. So, the gradient descent algorithm ensures that the first order approximation E hat W reaches its global minimum, but it does not ensure global convergence for the original cost function EW. So, in that sense, what gradient descent does, it tries to optimize the first order Taylor series expansion of first order Taylor series approximation of the original cost function. So, in that sense we only reach a local convergence. So, the gradient descent algorithm as usual is given by this. So, learning rate eta determines the speed of convergence. Convergence depends on proper choice of initial conditions, that I have already told you. So, now let us take a simple example of a gradient descent. EW is 0.5 W square minus 8 sin W plus 7. So, this is a nonlinear cost function. So, it is a multimodal function with 2 local minima and a global minima. The gradient descent update law for parameter W is obtained as this. Okay. So, delta W is minus eta del E by del W. So, if I differentiate this, I get eta, this is 2 into 0.5 1. So, W minus 8 cos W, and this is 0. So, that you see that this particular cost function, this is actually EW. So, this EW it has 2 local minimum and 1 global minimum. So, interestingly, if you look at the result is, if I use a adaptive value eta equal to 0.01, which you are seeing, that is a red one, circle one. So, if I start from this point, okay, W naught is minus 8, if I start from there. So, what I am seeing, that this comes and slowly converges at this point and does not go from there. So, it actually converges to local minimum. So, if I start from here, I reach here. But if I change eta equal to from 0.01 to eta equal to 0.4, if I take, then my eta's step size, learning rate size has increased a little bit. So, you can easily see that this square one. So, from this point it jumps to this point, and from this point it goes to this point, and again from here until it converges to global minimum in this case. Okay. So, changing this eta, I am able to again reach in this case to the global minimum. So, when eta is 0.01, W naught is minus 8, the final weight W equal to minus 4 corresponds to local minimum. Okay. This one minus 4. When eta equal to 0.4 and W naught is minus 8, the local minimum can be avoided, and final weight ultimately settles down at global minimum, okay, at this point. So, I reach the global minimum, but this is a simple function, and because this is a simple function, we are able to show that by changing this eta intelligently we can reach it. Okay. But if the function is complex, we have no idea, we have no comprehensive method to reach the global minimum using gradient descent. Although heuristically we can reach, like near global minimum. So, observation, for small step size gradient descent gets stuck at local minimum. For larger step size it may come out of local minima and get into global minimum. Algorithm may not converge for larger step size as well. There is no comprehensive method to select initial weight W naught and the learning rate eta for a given problem, so that the global convergence is achieved. Okay. So that the global convergence is achieved. Okay. So, that is about gradient descent. Now, because gradient descent is very slow in its convergence, it does not guarantee global convergence. So, people thought about Newton's algorithm, where like in gradient descent the weight update law is such that it tries to find the global minimum of the first order Taylor series approximation of the cost function. Now, in Newton algorithm if we take the same cost function EW and again we expand its Taylor series and we take the second order approximation here. Okay. So, if we take a second order approximation, so and here let us define G as del E upon del W, the gradient vector, and there is a Hessian matrix that is defined as H, which is dou square E upon dou W transpose. So, neglecting higher order terms, we have following second order approximation of the cost function. So, this is the second order approximation. Here EW is the second order Taylor series approximation of actual cost function EW, okay, and that we write in this particular form. Okay. So, the all other higher order terms from this point onwards has been neglected. So, this is a quadratic function of delta W. The necessary condition for minimization of E hat W, which is a second order approximation of actual cost function, is given by del E upon del W is 0, which gives the following update law for weight vector, which delta W is H inverse G. Okay. So, that is, if I go here and if I differentiate this del E W by del W, okay, this is a constant term, goes away. So, differentiating this, I get delta W is H inverse G, H inverse G. Okay, this is my weight update law. Using Newton's logarithm. But unfortunately, of course, once I take this, you can easily see that E hat minus E W naught is always a negative definite quantity, provided, not always, it is negative definite only when H is positive definite. Okay. So, this is true provided H is positive definite, means H is positive definite. I hope all of you understand positive definite bit. If I take any vector x transpose H x, okay, if H is a positive definite matrix, this quantity is always a positive quantity for any except any null vector. You take any vector x, this will be a positive quantity. So, that is H is positive definite. So, in that from that sense, that this algorithm is not a foolproof algorithm, because even it does not guarantee locally stable unless H is positive definite. That is the biggest drawback of a Newton algorithm, but still researchers have used it because it is very fast. But you see that it requires, this weight update algorithm requires H inverse of a Hessian matrix. Imagine a normal network has at least hundreds of weights. So, W the minimal order is 100. So, H has at least 100 by 100, the dimension of H would be at least 100 by 100. I said not 100 by 100 because it is a double derivative. So, it is a huge, the dimension is huge, and inversion is computationally very expensive. So, in that sense, this algorithm, although we can use this algorithm to solve a simple cost function optimization, but in terms of a neural network, this is I would say it is an infeasible algorithm. We can't implement it because Hessian cannot be computed. It would take a lot of time. So, the Newton algorithm, starting with any initial condition W naught, iterate following equation until stopping criteria is met, which is W t plus 1 is W t minus H inverse G t. This is the Newton algorithm, and the discussion is that the Hessian matrix S t has to be positive definite matrix for all t. That has to be, we can't guarantee H all the time. Steepened descent method operates on the basis of a linear approximation of the cost function, while Newton's method uses quadratic approximation of the error surface around the current point W t. Computationally intensive as it requires matrix inverse and H inverse. For non-quadratic cost function E w, convergence is not guaranteed. This makes it unsuitable for training feed-forward network. Now, we will take the same example that we considered earlier. E w is a scalar. You see that w is a scalar. It's not, w is not a vector here, simply a scalar. So, it's a very simple function, 0.5 w square minus 8 sin w plus 7. And if I use the and then because w is a scalar, naturally del E upon del w is a scalar, which is g, and h is del E by del square E by del w square. So, that is also a scalar, and if and weight update law delta w is minus eta H inverse. So, H here is a scalar, so it is inverse into G, that is our algorithm, where G w is f dash w. See, this is not f, this is E dash w, this is E double dash, that is this dash represent, this is actually del E by del w, and this is del square E by del w square. Okay. So, this is this represent this, and this represent this, and using this, if you update, you see that for some initial condition when w naught is minus 6, eta is 0.01, the weight diverges. That is because H is not positive definite. So, in this case H is not positive definite. Okay. So, H is a scalar here, as obviously it is not greater than 0, it is a negative quantity, and when w naught is minus 7 and eta is 0.001, the final weight converges to local minimum here, and when w naught equal to 0, so this from, if you start from here you reach here, but if you start from here you reach here. Okay. The final weight converges to the global minimum, but then we really did not achieve much with respect to, in comparison to gradient descent, except probably the gradient descent even converging to the local minimum, whatever the number of steps it will take to go to the local minimum, probably using this Newton method you can improve on that speed, but no way the desired goal of learning is achieved by Newton method. So, observations are as follows: convergence to global minimum depends on the selection of proper initial condition w naught. Algorithm may diverge for unsuitable initial condition because h w is not a positive quantity, or in fact in general I would not say h is a scalar for our example, but in general H, the Hessian matrix, is not positive definite, okay, or is not positive definite always. So, because the condition is that H has to be positive definite for convergence, and that is not guaranteed. Global convergence is not guaranteed, as it uses only second order approximation. So, Quasi-Newton method. So, first of all, Newton method did not work, it does not really work, it is not that great algorithm. But I do not know historically why people used Quasi-Newton method, because it simply tries to simplify the algorithm, Newton algorithm, where there is a inversion of Hessian matrix, and Quasi-Newton method tries to do away with inversion of Hessian matrix. Instead, it computes an approximation of inversion of Hessian matrix H through a iterative method, that is Quasi-Newton method. So, Newton algorithm is Wt is Wt minus H inverse T Gt, this is Hessian matrix, and as we discussed, the computation of this is really very difficult, because H, the matrix order is very large, it is always order of 1000 the dimension. However, the computation of inversion of Hessian matrix is a major deterrent. Even if we see for some problem, this is very good choice, this algorithm is very fast in convergence, but then this matrix cannot be inverted very easily. So, Quasi-Newton method uses an approximation to the inverse of the Hessian. The form of approximation differs in different methods. At each step, the current approximation to inverse Hessian is updated by using new gradient information. So, the basic form of Quasi-Newton method is that this is my new weight is old weight plus alpha t dt, okay, and whereas this dt is an approximation of my function, that is H inverse gt. So, that is where dt is minus ft gt, okay, and this alpha t is selected in such a manner that if I put in the argument of E with W an additional term alpha dt, then this is minimized for alpha greater than equal to 0. So, what we try to find out that alpha for which this cost function is minimum. Okay. So, here f is an approximation to the inverse of Hessian H inverse. There are some researchers, Broyden, Fletcher, Goldfarb and Shano, they have given they have proposed an iterative form of this ft. You can easily see how cumbersome this algorithm is. It looks very bizarre in fact, but in any case this algorithm is much simpler than if you really want to compute H inverse. I don't want to go in details, but you can easily refer those of you are interested, those who are more interested to know in this topic further. So, then you can apply search the work of these 4 authors BGFS, and then you can figure out how they derive this ft plus 1 based on ft. Okay. This is an iterative approximation of H inverse. So, I hope that you understood what I said here, that in Quasi-Newton method we, instead of computing H inverse, we compute ft, and that is an approximation of H inverse, and in update rule is in this form where alpha t is computed by minimizing this cost function. So, here is the example of for Quasi-Newton method, a quadratic linear cost function, linear quadratic cost function, which is W transpose A W minus W transpose B, where A is 5 minus 3 minus 3 2 and B is 0 1, and I want to find out the weight vector W, which is naturally 2 by 1. What should be the weight vector such that EW is minimized. So, I start with the W naught is 0 0, F naught is identity matrix, and then D naught is the first iteration I get minus G naught, and that is 0 1 transpose or a column vector, and the alpha naught is minus G transpose naught D naught by D transpose naught A D naught is half, and therefore, W 1 is W naught plus alpha naught D naught. Actually, this is a little mistake in the symbol. This is not actually D, this is actually F, yeah, D, yeah, right, D is FT GT, so it is right. So alpha naught D naught is, so you in the first iteration I get W1 is 0 half. If I go to the second iteration, I get delta W naught is this, G1 is this, delta G1 is computed, G1 minus G naught, and you remember that I have that formula of F1. If you compute using this formula, you get this particular this is, you remember that this is this has to be a 2 by 2 matrix, that is approximation, that is the 2 by 2 matrix, that is the approximation to inversion of the Hessian matrix, and D1 is minus F1 G1, alpha 1 is given by 2, therefore W2 is 3 by 3 and 5. Because the objective function is a quadratic in 2, so in 2 steps I can find out what is the weight vector. So the weight values 3 and 5, W1 is 3, W2 is 5, this weight vector minimizes the cost function that we started with, this cost function. So in 2 steps you can solve this problem, but simple problems is all right, but and you get the right minimum actually, but it is a linear quadratic function. So any linear quadratic function can be easily of any order, we can easily solve using this method. This is Quasi-Newton method, but this method really does not work for when the cost function is quadratic but non-linearly quadratic. So in that if that is the state, these Quasi-Newton method or Newton method really do not help us much. Now we will talk about a gradient conjugate gradient method. This is another type that people really use. Conjugate gradient method is a method again that are I would not present its how this conjugate gradient method can be used for neural network. I will just let you know that the motivation behind conjugate gradient method. So conjugate gradient method can really minimize a quadratic cost function in n steps if the order of the quadratic function is n. Okay, that is, if my A is a n by n matrix, okay, that is my W is n by 1 vector, then in n steps I can reach the minimum of this function. Okay. So, and that is the motivation by which conjugate gradient has been formulated. So it is well known that the minimization of a quadratic function of this kind is achieved by W star is A inverse B. You simply see where A is a symmetric positive definite matrix and W is a n by 1 dimensional vector. Now here is a definition of a conjugate vector definition. So given the matrix A, we say that a set of non-zero vectors D0, D1, Dn minus 1 is a conjugate if D transpose I A Dj equal to 0 for all I and j such that I not equal to j. If this relationship is satisfied, then these sets of vectors D naught to Dn minus 1, they are all known as A conjugate vectors, and these A conjugate vectors are all linearly independent. So, for a given set of A conjugate vectors d naught d1 up to dn minus 1, update the parameter vector wt along the corresponding conjugate direction dt as follows, where this alpha t is computed as is selected in such a way that this cost function is minimized by the selection of alpha. So, find out alpha such that this function is minimized, and that solution is given by when alpha t is minus g transpose t g dt by dt transpose a dt, and where gt is del E by del W is the gradient vector, which is E dash W, and this is A W minus B for the original cost function. We are only referring to this cost function. We are not talking about any general cost function, but a specific cost function. E W is half W transpose A W minus B transpose W plus C. So, any cost function if can be written in this quadratic form, then only the alpha t is this, and with that alpha t we update the weight vector along the conjugate directions, which is known as dt, t equal to 0, 1 up to n minus 1. A successive direction vector dt are generated as A conjugate versions of successive gradient vectors gt as the method progresses. In the beginning we do not know what are these direction vectors. So, we can have a recursive relation for computing this direction vector. So, which is written as dt plus 1 is minus gt plus 1 plus beta t dt, where beta t is given by this formula. So, if you plug in there, so we compute recursively the direction vector, okay, dt plus 1 t equal to 0, 1 to until we compute n direction vectors. So, the algorithm is very simple now, that set t equal to 0, select initial point w naught. We are only considering a linear quadratic function, cost function, remember. So, g naught is delta E w naught. If g naught equal to 0, stop, else set d naught equal to minus g naught. Alpha t is the formula that we have already shown, that minus g transpose t dt by d transpose t a dt. So, this t means this not time, this is 0, 1, 2, 3, 4, 5, and wt plus 1 is wt alpha t dt, and so on. Gt plus 1 is computed. If gt plus 1 equal to 0, stop, because it has reached once gt becomes 0, then it is a minimum position. So, then beta t is this quantity, dt plus 1 is minus gt plus 1 plus beta t dt. Set t equal to t plus 1, go to step 3. So, this is and we continued. So, let us take a simple example. So, I would say that, okay, from here we go again to this point. So, from we computed alpha t, and then we computed beta t, okay, and then we again go and compute alpha t and beta t. Using alpha t we update the weight vector, using beta t we update the direction vector, and this process is repeated. Okay. I hope the algorithm is very simple. So, conjugate gradient needs to recursively compute two specific quantity, one is alpha t, another is beta t. Okay. And using alpha t we update the weight vector, using beta t we update the direction vector. This is the principle of conjugate gradient algorithm. So, let us take this example. EW is this particular. So, this is a 3 by 1 matrix. Okay. So, we should be able to reach the minimum by in 3 steps. So, you see that we go on computing various values. Alpha 1 in the beginning is 0.2778, W1 we found out this value, and then again we found out what is G1, beta naught, D1, alpha 1. So, using D1 and alpha 1 we compute W2, which is this vector, and then third step you have D2 and beta 1 and alpha 1, and using D2 we compute W3 is W2 plus alpha 2 D2, which is this, and this is actually the minimum. So, this W ensures that. So, in 3 steps, for if the quadratic function order is 3, then in 3 steps we can reach the global minimum. Okay. And every step we update the weight along the direction vector, conjugate direction vector, D0, D1, D2, D3, D4. Okay. So, you see that the first weight update was done along the conjugate direction vector D0. Based on D0 we computed D1, and along D1 the weight vector was updated. Okay. So, that is we got W2, and again based on D1 we computed what is D2, and along D2 direction vector we updated weight vector W, and we got this minimum. And this is this guarantees this, if it is a linear quadratic cost function, conjugate gradient scheme guarantees the global convergence. Okay. Of course, for linear function global convergence is not a big thing. What is important in this particular algorithm, that it says that in exactly n steps I reach the global convergence. So, researchers what they have done, they have used the variant version of this conjugate gradient scheme for nonlinear optimization function. So, a conjugate gradient requires no Hessian matrix evaluation, no matrix inversion requires, solve quadratics of n variables in n steps. Okay. But this can be this, the next one is that this approach has been applied to nonlinear function approximation as well. So, we will now talk about another algorithm. So, we talked about first gradient descent, Newton, Quasi-Newton method, conjugate gradient. Now, this is a very recent algorithm of Wu, who conceived a Lyapunov function. This is the Lyapunov function V, which is half E square. E is the normal cost function that we gave earlier in this class, which is yp dz minus yp whole square over all the patterns summation. So, that is E, and G is here del E upon del W. Okay. This is your G. So, for any general neural network, if this is my V Lyapunov function, then Wu shows that this particular weight update algorithm, you can see this is a very complex weight update algorithm, guarantees global convergence using Lyapunov function approach. But unfortunately, again like Newton method, although this guarantees, Newton method does not guarantee global convergence, but Wu's algorithm, that if I start with this Lyapunov function V, this one, if I start with this V and we update using this law, you can easily see that this is in this case here this V1 is E, in this case V1 is E, and all other things you know already. This is mu I is the identity matrix, sigma is a variable, del square this V1 is E, del W transpose, del V1 by del W transpose by this norm, again del V1 by del W A square. So, this V1 is E plus eta V1 square. If this is a very complex algorithm, but it ensures, he has Wu has provided a theorem that proves that this algorithm can take us to global convergence. Okay. But unfortunately, this cannot be implemented in real time, because you can see that for again the Hessian matrix problem is there. Okay. So, but I would show to you that how this algorithm can take you to global convergence for a simple nonlinear function, the function that we have already discussed, 0.5 W square minus 8 sin W plus 7. So, for this, if I consider Lyapunov function V is half E square plus G square, its time derivative is given by V dot Eg plus Gs W dot, where Gw is del E by del W, Hw is del square Ew by del W square, and choose the following parameter update law. So, this law is actually comes from this. So, for a simple when W is a scalar function, then this very complex weight update law simplifies, and this is very simple to update. So, W dot is k E square plus G square by E plus Hg. E is a scalar function, H is a scalar function, G is a scalar function, and W is a scalar function. So, it is very easy to compute. So, this makes V dot is minus k E square plus G square, is always negative definite. Thence the algorithm is globally asymptotically stable provided GW exists. So, what I am trying to show is that at least there is a theoretical algorithm that shows that we can reach the global convergence point, okay, or sorry, global minimum point. But unfortunately, although we could show it in a simple example and you can implement it, but if when the problem is that of a network size, a neural network, a practical network that solves a practical problem, then this algorithm cannot be again implemented. So, but let us see the example. So, here step size is 0.1 and this is your actual cost function, and you see that how you slide along this cost function, and from here it jumps and goes here. So, it does not stay here. This is not a stable point in this algorithm. So, it jumps from to here. Similarly, if I take step size 0.001, then you see that it comes here, and again from here it jumps to this point, again it goes and stops here. So, this algorithm shows that from wherever, whichever initial condition you start, you can reach always the global minimum point. This is very nice, but unfortunately it is not implementable. So, Wu's algorithm would ensure global convergence. For large number of parameters, Wu's algorithm require computation of Hessian matrix as well as matrix inversion, which are not easy to compute. So, now we would compare with our last class algorithm, in the algorithm that we proposed in the last class. This is our own work in this institute that we have done, that is adaptive learning rate. So, this is called Lyapunov function 1, Lyapunov function 2 algorithm. So, we will again take the same example, and my V1 is half E square, this is wrong actually. V1 is actually E1, and V1 dot is del V1 by del W W dot, and this can be written as not E1, E. So, E is half Yp d minus Yp whole square sigma. So, this is your V1. If I take that as a Lyapunov function, we have already discussed in the previous class what is our the weight update algorithm. So, for this simple example, W dot will be for if when W is a scalar, this is simply E by G, where G is del E upon del W, and LF2, if I use the LF2 algorithm where my V is not this is E, this is simply E. So, the V2 is half E plus lambda W dot square, then V2 dot you can refer to our previous class, and then we have W dot is this, and that ensures V2 dot is this, and we have already shown that how Lyapunov function 1 and Lyapunov function 2 algorithms are derived, and they have an adaptive reta. So, if we go to their implementation on the same example, you would see that using Lyapunov function 1 algorithm, you see that it comes from this initial point, and here it oscillates for some time and then comes back and settles in the global minimum. And similarly, using Lyapunov function 2, you see that we start from here, and again from this point again it goes to jumps to here and reaches global minimum. So, the Lyapunov function algorithm, which proposes a comprehensive method to find adaptive beta, and using what is adaptive beta, I am just changing the initial position such that I go towards the global minimum, and it is a very convenient method, and this works pretty fast, and this is implementable in any complex network, whatever the network size is there. We have already discussed this thing. So, finally, the observation is the Lyapunov function algorithm gives rise to adaptive learning rate. This helps in avoiding local minima, computationally simple as they do not involve matrix inversion, but not globally convergent. Gradient descent. So, finally, the summary: gradient descent, it has a constant learning rate, slow convergence, prone to getting stuck in local minima, convergence depends on initial condition. Newton method requires inversion of Hessian matrix, computationally intensive, does not ensure global convergence because of quadratic approximation, convergence depends on initial condition. Conjugate gradient method avoids computation of Hessian matrix and its inversion, ensures convergence of quadratic cost function only. Lyapunov function algorithm gives an explicit form of adaptive learning rate, ensures Lyapunov stability of algorithms, improves the convergence speed, but not globally convergent. We have not been able to prove that our algorithm is globally convergent, but we say that the convergence property of our algorithm is much better than the present schemes. And use algorithm ensures global convergence, however computationally complex, requires computation of Hessian matrix and its inversion. So, it is of theoretical interest only now. Of theoretical interest. Okay. So, with that I conclude this lecture saying that we a kind of in this lecture we covered almost all variant of weight update rule that can be applied in neural network. So, you should have now a better exposure to look for if you are interested in developing a new weight update rule for any of these neural network that we have talked about, feed forward, feedback network. I hope that this class would help you. Thank you.